So then let's go to the to optimization. But before I can start this, I want to briefly recall some notation that we looked at a bit before, which is interval notation, and then I would like to point out what a continuous function is. And then we can go to the optimization itself. So we saw this before actually. So this just is to remind you what an interval is. So an interval basically is a set of numbers between two boundaries. And what's important here is that we can distinguish between the fact intervals which have their boundaries included or which do not have their boundaries included. And if you remember, if you do not want to include the boundaries themselves, so an interval between a and b, where would be an example, anything between -1 and 2, but not including a and b themselves. So x is not allowed to be -1 or allowed to be 2, but should be strictly in between these two numbers. We call such an interval an open interval, and oppositely, if a and b are allowed in, so x is to be any number between a and b themselves included, we call this a closed interval. So here's an example of that with 3 and 4 are actually also allowed. So that would be this interval, and it's actually denoted by this square brackets notation. So these were finite intervals in the sense that they were between two finite values. There's also unbounded or infinite intervals. An unbounded interval would actually either go all the way up to infinity or all the way down to -infinity, or both, right? If it's the whole number line, it would be infinity in all directions. So those intervals we would call unbounded, and all the other ones would be called bounded. So we have bounded, closed, open, unbounded. Those words actually I wanted to recall before we go into optimization. One final point I'd like to make is what's a continuous function again, actually. So we call a function continuous. Well, basically speaking, if a function is continuous in an intuitive sense, if you draw the graph of this function, you can draw this graph without taking your pen off the paper. So it's basically you can draw it as one single line without any jumps. A discontinuous function, so a function which is not continuous, there would be a jump here. So this right hand side, there would be not a continuous function or a discontinuous jump function, because when you come here, I'll go all the way up close to a, x equals a, but at x equals a itself, this function turns out to jump up to this new value here and to head on from that point on. So this is a continuous versus discontinuous function, and in particular what we're going to look at in the next bit is going to be important, that we'll be looking at continuous functions and not at discontinuous functions. So with that said, let's go to optimization. Let me first motivate why we do this. Well, this is basically something that optimization is basically finding the maximum or finding the minimum to some mathematical problem. That's one of the core uses essentially of mathematics in economics, but also in various other fields. So what you know this, of course, in your microeconomics course, you have been looking at profit maximization, finding price or the quantity such that as a firm you're maximizing your profits. That's an optimization problem for the firm. If you're in finance, you might be in portfolio optimization. You might want to find the lowest risk portfolio, for instance, or in other words, you want to select those stocks and those weights to different stocks into your portfolio, such that, for instance, the total risk or the total variance of your portfolio is minimized. If you look at the problem of capital structure in corporate finance, you might be interested in how should I choose my debt and equity ratio so as to maximize firm value. And the end with outside of economics, of course, you might want to find, for instance, the shortest route to a destination. Again, that's a maximization or minimization problem, actually, in this case. That is solved by your Google Maps or your TomTom or whatever you use to solve that problem. So many of these optimization problems, they can actually be formulated as mathematical problems in the form of we have some function, and I'm interested in, well, what's the maximum or the minimum value of this function, and at what input, so at what value of x, is this maximum or minimum attained. So we'll sort of have to figure out, we want to figure out ways of finding such an optimum to a particular function that we're given. And that's what optimization is all about. So let me be a little bit more precise. So we would like to look at extreme values of a particular function. So if we have some function on an interval in particular, so we typically be looking at functions on a given interval, what we call the extreme points or the extreme values are the maxima and minima of this function. So but when is a point a maximum? Well, this point C of this particular function corresponds to the maximum for f. Why is that? Well, because at every other point, not C, the function value is actually lower or as low. So this is sort of a tricky nuance here. So if there's other points which have the same value, so equals is allowed here, we still call this a maximum. That's sort of particularity of mathematicians, if you wish. So maximum points in all other points will lead to values that are, well, lower or equal to the function value at this point C. Then C is a maximum point. And similarly, the point D on this right-hand side figure is the minimum point for f, because for all other points within these intervals for an x that's not D, but within the interval, the function value is at least as high as the function value at D itself. So that's what's called the minimum of this function f on this particular interval. So that makes sense, I suppose. It sounds intuitive. But another thing to notice is that if you can actually find the maximum point of some function, of any function, then we can always also have the same method of also finding minimum points of functions, because the maximum of function f is automatically the minimum of minus f. So if somebody asks you, well, what's the minimum of function g, and you say, well, I don't know about minimum, I only have a methodology for finding maxima, well, then that would correspond with the maximum of the function minus g. So let's have a look at the simple function here. This is just a parabolic, a second degree function, quadratic function. So let the function g be defined here as this 3 plus x minus 2 squared. And now the question is, well, can we indeed find the extreme values of g in its natural domain? So when is this function maximal and when is this function minimal? Those would be the extreme values. On the natural domain, well, perhaps you should first figure out what's the natural domain here. Well, this is a function for which any value of x is obviously allowed. So the natural domain is just the whole number line. Any real number x is going to be allowed here. So what can we do? Well, we might notice that, well, this function g has a special form, is written in a special form. It's 3 plus a squared, basically, x minus 2 squared. And we know that squares are always positive or 0. So this second bit here, the x minus 2 to the power 2, x minus 2 squared, that's always going to be positive, except of course when x minus 2 equals 0 or x equals 2. That's going to be 0. That's the lowest where x minus 2 can go. It's always higher than 0 or 0. But what does that imply? Well, that means that this function g will always be at least equal to 3. And it will attain this value of 3 only when x equals 2. Because then the second term will be 0, and function g will equal 3. So you conclude that g has a minimum here. So g has a minimum of 3, and it occurs at the value x equals 2. So we also we're wondering about all the extreme values. So might this function also have a maximum? Well, I think it's fairly easy to convince yourself that if x goes away to infinity or minus infinity, this x minus 2 squared is going to be a very large number squared or a very negative large number squared, but not either way, it's going to be very large and as large as you wish actually. So there's actually no value that you can never surpass. So you just go a bit further to the right or further to the left and you will have an even higher number. So there's actually no maximum to this function g. It only has a minimum occurring at x equals 2. And we can see this in this particular graph. So this is of course not drawn on the whole domain. We couldn't do that, of course. But you do see the minimum here occurring at x equals 2. Okay, and you see that's running away to infinity either way on the left or on the right hand side. So for big x and for small negative, for very large negative x, I should say. So another thing that I'm sure you remember from high school, if you read it again. So if we have a differentiable function, so a function that we can take the derivative of. So most functions that we'll be looking at will be differentiable functions on some interval. And if we know that c is some interior point inside this interval, so it's not on the boundary of this interval, but somewhere in between the boundaries, strictly in between these boundaries, then if this function is a maximum or a minimum at c, so if this function attains its maximum or its minimum at x equals c, this interior point, well then we know for sure that the derivative at that particular point should be 0. So f prime c, this should be 0. So essentially what we can see this happening here basically in this graph. We identified, and that's basically how we define the derivatives. The derivative of f we identified with the slope of the tangent to this particular graph. Well, what's happening at the maximum and what's happening at the minimum, points D and C in the picture. The tangent line is actually flat. You can see that. So the tangent line is flat and the tangent line in D is also flat. So what does it mean? If it's flat, its slope is 0. So in other words, the slope is 0, the slope of the tangent line is 0. Then we know that the derivative of this function, f prime, is going to be 0 as well. So if you have an interior point, which is either a max over here, or a minimum over here, then we know for sure if this function is everywhere differentiable, then f prime, the derivative of the function, should be 0 at those points. And those are actually our special points. They have a name. They're called stationary points, because basically the point is, if you're walking through this graph at this very moment, you're neither going up nor going down. So basically you're stationary in the y direction. That's the origin of that name. So if there's an interior extremum, an interior maximum, or an interior minimum, then this function, if it's differentiable, will certainly have 0 slope there or be a stationary point. Does the converse hold as well? The answer is going to be no. So it's not the case that every stationary point will correspond to a maximum or a minimum. So how can we see this? Well, here indeed the first stationary point occurs here at x0, so the slope of this line is 0, so the derivative is 0. It looks a bit like a maximum, but it's essentially what we'll see later, a local maximum only. The function definitely gets higher. If you go all the way up here, you attain higher values. So this is not the global, as it is called, maximum of this function. Likewise, at x1, again, the slope is 0, but this is not the global minimum of this function, because if you go all the way over here near this boundary, you reach even lower values. So again, x1, a local minimum, but not a global minimum. And even more particular here, again at x2, the slope of the tangent, which is this flat line here, is 0. So again, this is a point at which this function has a 0 derivative. But you see that it actually is comes here ascending, then it's flat for a bit, and then goes further ascending to the right hand side. So this is actually an inflection point of this graph. So these are 3 examples of points where the function is stationary. So the f prime in these points is 0, but none of these 3 points are the actual maximum or minimum of this graph. So if you look at this graph, you'll see where the actual maximum and minimum are. They occur at the boundaries. So this is the actual maximum of this point if it's included. And this is the actual minimum of this point, provided that A actually is included in the interval. So now we can say something about, at least about candidate points for extreme values. So if you have some function f, which is defined on some interval I, the candidate points for the maxima and for the minima will be, well, of course, the stationary points. I'm not sure, but if there's an interior point and it's stationary, then at least it might be a maximum or a minimum. Or put differently, if it is a maximum or minimum, then we know for sure it's stationary, so we better look at the stationary points. We saw that's not enough. The endpoints are also important. So in previous graph, actually it was precisely at the two endpoints of this interval that the maximum and minimum of the intervals occurred. And in the graph on this slide, we actually see that we can have another special point, which is a point at which this derivative does not exist. So this is sort of a spike here, a kink in this function. This function is actually not differentiable everywhere. It's not differentiable at this point D, and this is another candidate again for a maximum or minimum. In particular, for this particular example, we see from the graph that at this point D, where the function is certainly not flat, it's sort of we cannot say what the derivative is, right? It can be anything. So here actually the minimum occurs at the point D, while the maximum in this particular example will occur at the point B, provided it is actually in part of the interval. Okay, so these are the three kinds of candidate points. So if we want to find extreme value of a function, we'd better look at all the stationary points. We'd better also have a look at the endpoints of the interval, and we'd better also have a look, if they are there, at points in which the derivative is not defined. We cannot take the derivative of the function. It doesn't exist. So that brings us to another important question. Does every function actually have a minimum or a maximum, a function defined on a certain interval? Well, no, that's not will not be the case. So take a very simple example. Here the function f(x) equals x. So here you see the graph of this function. So it's defined on the interval, which is the whole real line. So any x goes. Does this thing have a maximum? Does it have a minimum? No. Is it a maximum? No, you can always get higher, right? If you just go further to the right, to larger values of x, you get a higher value of this function, so we'll never attain any maximum. So you see what's going wrong here. We can go running off all the way to infinity or to minus infinity and never really attain a maximum. So clearly we have to impose some additional conditions if we want to be sure that a maximum actually exists. So what makes sense here from this example, or this counterexample I should say, it makes sense to limit our investigations to functions which are actually defined on a bounded interval. So let me re-ask the question, does every function defined on a bounded interval have a minimum or a maximum? Well, if you listened carefully at the discussion on the previous slides, where we had sometimes maxima or minima on the boundary of the slide, and I was careful to say, well, they occur at these endpoints, provided these endpoints are actually included. So that's going to be important. Because if we're not including the endpoint, suppose we're looking at the same function here, but only confine ourselves to the interval between -2 and 3, which is these points not included, so indicated by these round brackets here. So we're looking at the open interval of all x between -2 and 3, but -2 and 3 themselves not included, then again we do not attain an actual maximum or an actual minimum for this function. Because we would like to say, yeah, well, the maximum is going to be attained at x equals 3 or very close to 3. Well, we never get there, right? So we can get closer and closer to 3, but 3 itself is actually not part of the interval that we're looking at. So the actual maximum is again not attained, and likewise for the minimum. We would like to say it's at -2, but -2 is actually not in the interval, because -2 is because the interval is open also at that side. So having an open interval can also ruin the existence of a minimum or a maximum. So we have to rule those out as well. So new question, a bit more specified. If we now limit ourselves to a closed and a bounded interval, so it's bounded, doesn't run away to infinity. It's closed, so the endpoints are included as well. Are we now fine? Will we be guaranteed to have a minimum or a maximum? Almost, but not quite, because we've still forgot one condition. Look, for instance, at the function 1 over x. Let's, the graph is like this. On the right hand side, it's this hyperbola. On the left hand side, it's this hyperbola. What's happened at 0? Well, the 1 over x itself is not defined there, of course, but we can just add this number separately to this function. We say, well, if x equals 0, it's not 1 over x, but we just define it to be 0. So this point in between here will also be part of this function. So it's a nice function. It will sort of give us a number, so we can look at this function on the interval -3 to 3. Nice bounded interval. It's also closed, so we're careful to include -3 and 3. So this is a closed and bounded interval. We have this function. Does this function have a maximum or a minimum? No, it doesn't. So we can get as high as we want by going as close as we wish to 0, but not actually to 0 itself, because there we define the function to be 0. And likewise, if we're on the negative side, close to 0, go all the way to minus. The function goes all the way after minus infinity. So though the interval on which this function is defined, so its domain is closed and bounded, the range is actually not bounded. It runs away all the way to infinity. So what are we missing? Well, of course, this function makes this sort of enormous jump at this value of 0. So we don't want a jump in the function either. So remember what we call the jump. Having a function with a jump was not continuous, right? It was a discontinuous function. So what we would like to add as well, let's rule out these cases by confining ourselves also to continuous functions which do not have any jumps. So question, does every continuous function defined on a closed and bounded interval have a minimum or a maximum? And now the answer is no, it does. Yes, it does. So that's where we are, and this is the going to be the extreme value theorem that we'll use extensively when we're actually looking for maxima and minima in the next video. So there we are, and that will be the next video.